DC circuits, Kerkoff's rules. Up until this point, you've been taking circuits and applying your rules for series and parallel resistors and series and parallel capacitors, and reducing the circuit down to something that you could deal with and solve for, and then sort of expanding it back up, working backwards to find the currents and the voltages and the charges on the various devices. But try doing that with this circuit. Here we have 3 resistors, 2 batteries, a fairly simple circuit. Are any of those 3 resistors in series with each other? No. Are any of those 3 resistors in parallel with each other? No. So our rules for series and parallel resistors aren't going to help us here. This circuit is as simple as it gets according to those rules, but yet we still can't quite solve it. So we need another tool in our toolbox. We need Kerkoff's rules. So step 1 is to choose the directions of the currents in each branch of the circuit. And you don't have to know anything here. We can just guess if we want to. Normally, we know that the positive side, the current comes out of the positive side of the battery. So I'm going to go ahead and put in for the first branch here, with the branch that runs from to the first battery, V1, and through the first resistor and back up to that other junction, that branch. I'm going to call that current I1, and I'm going to say it's going up through resistor R1, which means it's going to the right over there on the top, and it's going to the left at the bottom. Everywhere in that part of the circuit has the same current, right? I1, and I'm choosing up through resistor R1 as my direction. And in my second branch here, the middle one, I'm going to say the current is going up through R2, and I'm going to call that I2, and that's the same down here, right? Basically, we're starting, there's a junction here at the bottom, and there's a junction here at the top, and so from one of those dots to the other one, straight up through the middle is I2. And then just to show you that you can get these wrong, and you don't have to guess correctly, I'm going to guess that my current is also going up through R3. I'm going to call that I3, which means it's going to the right in the bottom part of that branch, and it's going to the left in the top part of that branch. And I know that one of these has to be wrong because I can't have current coming in from all 3 of these directions into this junction and nothing coming out. It's like the flow of water. Current is very similar. That's why we use the term current for both water and electricity. It's like having 3 hoses, all with the water coming into some junction and nothing coming out. Well, that's not going to work for very long, is it? So I know for sure I guessed wrong on one of these, and I did that on purpose so that you can see what happens in the end. You don't have to guess correctly, just guess the direction of the current in each branch. That's step number 1. Step 2 is to indicate on your drawing which side is the high voltage side and which side is the low voltage side for each device. So we have some rules for this. Let me slide down. Yeah. If it's a resistor, we look at the direction of the current. I'm going to have my current going this way through the resistor. And we know that current is the flow of positive charges. So if a positive charge flows from the left side of my resistor to the right side of my resistor, what direction do positive charges go? They always go toward lower potential. So the left side of this resistor has to be at higher potential than the right side, or the current wouldn't be going in that direction. If both sides were at the same potential, I'd have zero current. If the right side was at higher potential, the current would be flowing right to left. But if I know the current is flowing left to right, then the left side has to be at higher potential than the right side, or the current wouldn't be going that way. So I look at the current to determine which side is at higher potential for my resistors. For my batteries, for my power supplies here, my DC power source, I look at the drawing. The longer line is always the positive side of the power supply, and the short is always the lower voltage, the negative side. So it doesn't matter which direction the current is going, the longer line always is the higher potential side. So let me go back to my drawing, and I'll put these indicators in there. And this is one of those things that, if you do 100 of these, well, maybe not that many, but if you do a whole bunch of these problems, eventually, you can skip some of these steps. But really, when you're starting out, just do each step. This is a very easy process. Kerkoff's rules are very easy. You don't want to miss this problem on the test. They don't get much easier than this in physics, but you've got to know the details, and you've got to just be careful. So if you follow along and you get the details down, you'll get the problem right. So let me go. First, I'm going to do my batteries. This is my high potential. This is my low potential. High potential, low potential. And then my resistors, I look at the flow of current. So for R1, my current is going up. So the bottom of R1 must be at a higher potential than the top. The bottom of R2 must be at a higher potential than the top because the current is going in that direction. And the bottom of R3 must be at a higher potential than the top of R3. So these are just to help you later, as you're doing your loop rule, figure out whether you're adding or subtracting, whether that potential difference is positive or negative. Step number 3 is to apply the junction rule. So what is the junction rule? Basically, it says that the sum of all the currents at a junction add up to 0. Or another way of writing it is the sum of all the currents into the junction has to equal the sum of all the current out of the junction. So if we're calling the current into the junction as positive, then the current out would be negative, or vice versa. But let's pick a junction here. I'm going to pick this top one. I'll call that A. Junction A. And what do I have? I've got I1 coming into junction A. I have I2 coming in, and I have I3 coming in, and I have nothing coming out. So what I get when I apply the junction rule to point A, I get I1 plus I2 plus I3. That's what's coming in, and I have nothing coming out. So that's my first equation. If you take a look at this problem, you'll see we have 3 unknowns, I1, I2, and I3. And if we have 3 unknowns, we need 3 equations to solve for them. And this is our first equation. And a pitfall that a lot of students fall into is they do not apply the junction rule. They go right to the loop rule, and they use 3 loop rules. And that does not work. You must use a junction. This has to be one of your equations. A junction rule has to give you one of your equations. And step number 4 is to apply the loop rule. So what's the loop rule? It's the sum of all the potential rises and drops around a loop is 0. Or another way of stating it, the sum of all the rises has to equal the sum of all the drops. So if you call a rise positive delta V and a drop negative delta V, then you add them all up as you go around a loop, you'll get 0. Or the rises have to equal the drops. Another way to think of this is sort of like going on a hiking trail, and think of delta V's as elevation changes. If you go up a hill and then down a hill and then up a flight of stairs and down a flight of stairs and over some more, and you go around this long loop hiking trail and you end up back where you started, you have to be at the same elevation again. So you add up all your elevation rises and all your elevation drops, and they better equal 0. Well, the same thing is true with the circuit. Let's take a look at our circuit here. If I start, let me pick a color. How about yellow? If I start in this corner, the lower left corner, and I start walking around this circuit, I go up by some potential through that battery. Then I'm going to drop by some potential through this resistor because I'm going in the same direction as the current. Then I come over here and I'm going up in some potential because you can see I'm coming into the resistor at the low potential side and I'm coming out at the high potential side. So I'm actually going up, and then I'm going down through this battery. I'm going in at the high side and coming out the low side, and then I come back to my starting point. And we can call that loop 1. So if I start out at some point and I go around the loop and I come back to the same point, I better get back to the same potential. So I can add up all the rises and drops around that loop, and I better get back to my starting point. So let me do that for you. So this is going to be loop 1. The first thing I went through was that battery, right? I went up. I'm going to put a positive. I went up by V1. Let's go back and look at it one more time. I went up by V1. I went in the low voltage side, came out the high voltage side. So I went up by V1. Then I went into this resistor. I went in the high voltage side, came out the low voltage side. So I dropped by whatever the potential drop is across a resistor. And that's just I times R. So in this case, it's I1 times R1. So I dropped by I1 R1. Then I went into another resistor, but this time I'm going in the low voltage side and coming out the high voltage side because I'm going opposite the current. So I rose by its potential difference. I rose by I2 R2. And then I went through the last battery, but I went through in the opposite direction. I went in the high side, out the low side, so I dropped by V2. And then I got back to where I started, so I add up all the rises and the drops, and I get 0. So don't fall into the trap of thinking that every time you go through a battery, it's a rise. In this case, we went through one battery in the right direction, and it was a rise. We went through the other battery in the opposite orientation, and it was a drop. And don't fall into the trap of thinking every time you go through a resistor when you're applying Kerkhoff's rules, it's a drop. Because when you're going with the current, you're right, it's a drop. But when you're going opposite the direction of the current as you walk around the loop, it's a potential rise. So you've got to, that's why I put the pluses and minuses in there, to help me get those straight.